All right, good evening, everyone. It's now 5 p.m. Brisbane time. Currently enjoying, currently enjoyed the first 24 hours of lockdown in Brisbane. So yes, this evening I'm starting to take over the lectures from Yoni. I'm starting with chapter 5 of the course reader. Now, I will be using slides, my own personally prepared slides for this course, but you shouldn't worry too much. All of the content, basically all the content that I'll be delivering through the slides, I've essentially ripped from the course reader. So there's basically nothing new in the slides that aren't in the course reader. Furthermore, I will be uploading these slides to GitHub, both the annotated version that I'll be going through in the lectures, and also the more pure version that doesn't have any annotations. So yes, I'll be going through units 5 to 10. Hopefully, most of that with you in the remainder of the semester, and hopefully we can all enjoy our time together, and we can all learn a lot. Please do feel free to interrupt via the chat with questions as you have them. I'll endeavour to answer questions that arise in the chat as I see them, but I'll also endeavour to pause after key moments and invite questions if that works out. I'm also hoping that occasionally throughout the course of my lectures, there may be opportunities for me to ask you guys questions, hopefully with simple responses that I might ask you to just use the chat to respond. So we'll see how we go with those. Okay, so unit 5, this concerns sequences, limits, and series. So essentially, I see all of units 5 to 10 as introductory calculus. You may have studied calculus in your previous exposure to mathematics, but yes, calculus is essentially the name of the game. So all of the textbooks listed in the course profile that explicitly mention calculus will probably be useful to keep an eye on if you want extra help with problems, or really any textbook you find that claims to be an introduction to calculus, you might find valuable when going through this particular part of the course. Okay, so that is essentially my introduction. I wondered if anyone had any questions at this point. I'll only give a brief amount of time for questions right now. All right, so I'll move on. So yes, let's get on with the content. Sequences, limits, and series. The first thing I want to do for you is actually, hopefully I'll be able to convince you of the need to actually consider sequences. So this is actually the first instance in which I will ask for audience participation. When you see this question, what is the area of a circle of radius 1? What do you think the answer is? There's essentially, I would guess that I'm only going to see maybe one of 3 different answers here, but whatever pops into your head right now, could you please put that in the chat? So we've got an answer of pi, another one of pi. Are there any other answers? All right, so it seems like we're stuck with pi, and yes, of course, the answer is pi. Oh, sorry, there was another answer I didn't see. One of the answers was x squared plus y squared equals 1. So that's certainly a good description of the unit circle. Okay, so as you all have pointed out, the answer to this question is indeed pi, but I want to go a little further here and ask, what is the actual number? So I won't ask you to respond to this. The number of course, well, people recognize that the number is something along the lines of 3.14, and then at that point they'll write ... So let me write that. The answer, people might think that 3.1415 ... is the answer, but my issue here is this ... thing. The thing is that pi is an irrational number. You may have heard of that term, irrational, before. Essentially what that means is that it's actually impossible to describe the number pi exactly. The only thing we can do with it is approximate it. So 3.1415 is actually a pretty good approximation. Now the question is, how can we actually find such an approximation? What sort of machinery do we have available to us? This is an exercise you may have done in high school, perhaps, where you would have approximated what pi is by breaking up the circle into areas that you might be able to find the exact area of. So this is an example of breaking a circle up mostly into triangles, and presumably we can all work out what the area of these triangles are. Unfortunately, we're still missing some bits that we won't quite get with this approximation, but nevertheless, the hope is that what we're missing out is small enough for us to be satisfied that the number we end up with is actually a reasonable approximation. Now, this question has actually been of fundamental interest to mathematicians all throughout history. Perhaps some of the earliest records that we see of attempts to describe what this number pi are can be traced all the way back to the Babylonians. I think one of the first reasonable recorded approximations to pi is the number 3. This has been attributed to the Babylonians. What's also interesting is that in the Hebrew Bible, it's known that 3 was used as an approximation for pi. One passage in the Bible was discussing a certain cylindrical object in the temple, some particular temple, and a radius of 1 was given, and it was instructed that you would need 3 units of area to cover the top of this. So that's quite interesting. Of course, we get better and better approximations of pi as we go through history. We have this famous 3.14 approximation that is used quite often. This was developed as early as a couple of hundred years into the Common Era. All right, well, jumping into the 6th century now, we've now got a couple of extra digits here, so that's good. The point of this slide is to emphasize that, you know, the approximations just keep getting better and better. Wow, this is a bit of an involved approximation. I shudder to think how much work would have gone into actually constructing that number. All right, now jumping ahead a bit to modern times, we have an approximation of pi that's correct to 31.4 trillion digits. Of course, it would be impossible for me to actually write down this number, but the point is that this was done quite recently. There's a Guinness World Record involved with calculating digits of pi, and in 2019, this was broken by a Google employee. Now the question is, how could you possibly get an approximation that good? Well, she didn't do it by hand, perhaps unsurprisingly. She used all the resources she had available to her. She set up some machines with the Google Cloud, and it took her 121 days using these machines to actually calculate the number. So I've got some fun comments here. Wow, cash burning. Yes, I wonder if the taxpayers would be happy about the fact that, well, who would be interested in that? And another question, why would she do this? Well, as I said, there's a Guinness World Record associated to this. So maybe that's one motivation, to show that she could perhaps, but also, yeah, comment here, Google employees surely have too much free time. I would say that this is one interesting thing of itself is to show just how far computers can be pushed. So what's really interesting here is, and what might be interesting to you, is that up until this point, everything was done by hand. But as soon as computers get involved, we can really push the limits of human knowledge. And so one of the important things you do with data science is sort of marrying these ideas together, using good ideas from mathematics and combining them with machines to really produce outstanding results. There is actually another one here. Someone took this record from her, I think even last year, pushed it all the way to 50 trillion digits. So that's quite phenomenal. I can't remember who did that one. But the point of this is that as technology improves, we keep getting better and better approximations of pi. But here's the thing of it, we will never actually know what it is exactly. We'll never be able to describe it to correct to 0%. There's no way that can be achieved. And that's basically a consequence of the fact that pi is irrational. There's a question here, I presume that question is, where can we download this PowerPoint? So the answer to that is once I've completed my work, once I've completed the lecture tonight, I'll probably find some time to upload this to GitHub tomorrow, hopefully. So I hope that answers your question. All right. So this, I think, is basically explains the need for sequences, because sequences have this idea of, getting arbitrarily close to the true number, but never actually being able to get it. So perhaps for an example that's a bit more concrete for you, along the lines of types of problems you may have encountered previously, consider the following problem. I'm giving you a function, f of x equals 1 plus x cubed minus x to the fourth. I want you to find me a root of this particular polynomial. And what that means exactly is that I want you to find a positive number x, so that f of that function is 0. Okay, so I've taken the liberty of graphing this function here. So it's this of using a Desmos online graph creator. I've put that function there, and this red line is exactly that function. And so you can see that, well, there seems to be a 0 around about here somewhere. So that's great. But again, what is that number? Okay, well, to give you some idea about what this number is, I've plotted the vertical line x equals 1.5 down here, and I've plotted the vertical line at 1.7 down here. Now, the thing is, this 1.5 line intersects with the graph, with the curve above the x-axis, whereas the 1.7 intersects it below, somewhere down here. So from that, we could conclude that, well, I can't say exactly what the answer is, but I think it should lie between 1.5 and 1.7, and that would be correct. That basically gives you an approximation to your solution. Now the question is, can you do any better than that? Okay, well, to get an idea, all I've done from this slide to the last one is I've zoomed in. So I've basically just used the zoom in function on my computer. I've zoomed in, and now I get a better picture. So it's the same three lines drawn here, but now it looks like we can do a bit of a better job in actually finding what the root is. So let's update our estimates here. So last time we had 1.5 and 1.7. This time I've shifted my left approximation to 1.6 and my right one to 1.63. So I've got some good comments here. 1.6 to 1.7. Yes, that's an intermediate approximation to the one I just used. And we also have a question about whether or not this is a bisection method. And this is not exactly the bisection method, but it's certainly along similar lines to what you're suggesting there. Okay, So if I graph the 1.6 to 1.63, I see that once again, my true solution is between 1.6 and 1.63. So that means I just obtained a better solution. Well, can we do even better? Well, yes, we can. I've zoomed in yet again, and this time I'm approximating with 1.616 and 1.619. And at least according to this graph, the graph is suggesting that the true solution lies between here. So the point of me doing this is to convince you that it is in fact possible to get your answer as accurate as you desire, but it's kind of hard to know what it is explicitly. Now, you may think, it may be the case that you've just quickly taken this polynomial and put it in Mathematica, and it would have told you that what the solution is. The solution to this particular problem is 1 plus the square root of 5 on 2. So this is exactly the number I was trying to approximate. Now you might think, well, if you've got the exact solution, why did you bother with this approach that you were just taking? And the reason is, excuse me, even though I can write down, 1 plus root 5 on 2, root 5 is another one of these irrational numbers that cannot be described exactly. It can only be approximated. So this is the point of all this. I obtained a collection of numbers which I think are lower bounds on the solution, and I obtained increasingly good upper bounds on the solution. And the thing is, I could keep doing this, but I'd never know what the true solution is. So this I hope, motivates the need for sequences. Now, you may notice I haven't actually told you what a sequence is. A sequence is basically just a collection of numbers, but there's some sort of order lying in the background. So on the previous example, the sequence of numbers would have been the sequence of numbers obtained by getting better and better approximations. So sequences is basically just a collection of numbers, except the order is important. Okay, let's try and be a bit more formal about this. Sequence, definition of a sequence. It's an ordered set of real numbers. Typically what you do when you describe a sequence is you write down the elements of that sequence and you describe them according to their order. So you would have A1, A2, all the way up to AN. Now, in the case that n is finite, you could actually write down all of the elements in that sequence. But be careful, because sometimes you could be dealing with an infinite sequence. So that means you've got infinitely many of these numbers that you've got to keep track of. Okay. Now, once you've got your collection of numbers from A1 up to AN and possibly infinity, the sequence itself is typically denoted with this notation here. So the way you say this is by saying, the sequence of numbers AK with A running from 1 up to N. And again, I'll remind you that N could actually be infinity. Okay. Now, each of these AI numbers or AK numbers, in this case, they're referred to as the terms of the sequence. So, and each of these terms gets a number depending on how far along the sequence they are. So for example, if you've got the sequence containing numbers AK, for K running from 1 to N, then AI, for a given number I, that's referred to as the ith term of the sequence. So for example, in this example here, A1 up to AN, A1 is the first term of the sequence. A2 is the second term of the sequence. Now, we need to be a bit careful here, because while it's great if we have a sequence like this, sometimes we might have a sequence where the sort of subscripts start a bit off. We could have a sequence of numbers that start with A0, then go A1, and then A2, and so on. This time, A0 is actually the first term of the sequence, and A1 is the second term of the sequence. So in this particular example, AI is the ith plus one term of the sequence. So hopefully all that makes sense. Hopefully, in order to give you an idea about what sort of sequences actually look like, I'll be looking at some examples of some sequences now. And the first example I want to describe to you is actually a sequence that we started off with, the digits of pi. Okay, so as an example of a sequence, I'm going to define a sequence of AK for k running from 0 to infinity. It's going to be the sequence so that each individual term, each AK term, is the number pi, except, well, we don't know what pi is exactly. So it's pi corrects to the first k decimal places. And so in this case, our sequence would be 3, that would be the first term, 3.1 would be the second term, 3.14 would be the third term, and so on. So this is actually an infinite sequence, but there is a catch here. And the catch is that even though this is an infinite sequence, it's actually impossible. At the moment, it's impossible to write them all down because we just don't have the computing power. In fact, as of modern times, as of today, I think the furthest we could go along in this sequence is to the 50 trillionth a term in this sequence. So that's one example of a sequence, and the way of describing what mathematicians have been doing throughout the centuries is actually trying to find this sequence. So Babylonian times, we started here, and as we moved on through the centuries, we were able to get further and further along into the sequence, but we were never able to know all of the terms of this sequence. Okay, so that's pi. Maybe for a slightly more relevant example of sequences, we're going to have a look at ancestors. So I'm going to define a sequence consisting of terms AK for k running from 1 to infinity. And I'm going to define it to be the sequence of numbers so that the AK number is the number of ancestors you have at a generation of k above you. So more concretely, what does that mean? Well, it means that A1 is the number of parents you have, and A2 would be the number of grandparents you have, and this would keep going. So of course there would be some exceptions to this, but in the generic case, you would have 2 parents, 4 grandparents, 8 grandparents, 4 grandparents, 8 great-grandparents, and so on. So the first term of this sequence is 2, the second is 4, the third is 8, and we keep going. So this is one way of describing a sequence, but what's really nice about this is that there's actually a really concrete, and even better concrete way of describing the sequence. If you've looked at the notes ahead of time, you'll know that you can actually write this explicitly with the following formula. If you're looking at the term AK, then AK is exactly the same as 2 to the power of k. And this is true for each k that's a natural number. Okay, so that's pretty nice. Now, what's so nice, in fact, this is so nice that we've decided to give a name to it. If you've got a sequence and you can actually write down something explicitly like this, you can actually say AK equals something explicitly in terms of k, then we would say that this is an example of a general formula for a sequence. So a general formula for a sequence, you get one of these anytime that you can just explicitly write down your terms AK in terms of the number k, which describes how far along in the sequence you are. Okay. Now, I'll leave a brief period for any questions that people might have at this stage. All right, I'll keep moving on. Okay, so question. Thanks, Xiaowang. Okay, question. Let's suppose we've got one of these sequences, k equals 1 to infinity, and let's say we do actually have an explicit formula, a general formula for the sequence. This question, mostly just a computation, computes the first 4 terms of this sequence. Okay, well, we're told the sequence starts at 1 here, so that's what this one is telling us. So what this is saying is compute A1, A2, A3, and A4. Well, we're able to do this because we've got an explicit formula here. So how does that work out? Well, for each k that we're interested in, k equals 1, 2, 3, 4, simply put k, that choice of k here, here, and here, and we'll get our answer. So k plus 1 becomes 1 plus 1, k becomes 1, and k plus 3 becomes 1 plus 3. If you work all that out, you'll end up with a quarter. So that means the first term of this sequence is a quarter. What about the second term? Well, you can play this game again. This time k becomes 2. And when you add all that up, you'll get a minus sign at the front, 2 on the top, and a 5 on the bottom. So that's minus 2/5. And of course, we can keep playing these games. We find that the third term in this sequence is 1/2. And we find that the fourth term in this sequence is minus 4/7. Okay, so that was a question asking you to somehow jump between a general formula for a sequence and actually writing down the terms explicitly without a reference to k. Okay, so I've got a couple of comments here. Sorry, one comment. Can you give some examples of applications of series? So Kai, is this, when you say series, do you mean, are we talking sequences, the things that we're doing right now, or are we talking about series, which comes up later in this unit? Sequence. Okay, so this is an example of a sequence here, and you're asking for an application. Sorry, I see. You're asking for an application of sequences. Well, I think that the best application I can give you for that is actually one that we did earlier. The sequence, this was an example of a sequence here, the sequence of getting arbitrarily close to a solution. So quite often basically many applications in mathematics and science can boil down to trying to find a zero of a particular function. And more often than not, it's actually impossible to write down the solution explicitly. So the best we can do is actually, well, we can't write down the solution exactly, but what we can do is give approximations. And the best way to describe approximations, I believe, are with sequences. Now, that might not be satisfying for you, Kai, because we already went through this, but hopefully we'll see some applications of sequences later on in this unit. So let me know at the end if you're unsatisfied. Okay, so we were here. Okay, now question. This time we've got a sequence, k equals 1 to infinity. The first 5 terms are -1, 4, -27, 256, and -3125. Now, this is an interesting question because we're told we've got a sequence consisting of infinitely many terms, but we've only been given the first 5 of them, and it asks us to find a general formula. Now, this in some sense can be a trick question because, well, if you're only given the first 5 terms of a sequence with infinitely many numbers, there are actually heaps of different ways of writing down an explicit formula. So for example, you might just be able to find a fifth order polynomial that manages to hit all of these points, and that would be your explicit sequence here. So while there are heaps of options, I'll just be giving you one particular correct answer. So in order to try and get an idea about what such an explicit sequence would look like, we notice that, well, the minus and plus seems to be alternating. And so when we see minus signs alternating like that, what we really should be thinking of is this minus 1 to the power of k term. Because minus 1 to the power of an odd number is minus 1, whereas minus 1 to the power of an even number is actually just plus 1 itself. So that means that, well, we could expect that our sequence looks like minus 1 to the k times some other sequence, except this time this sequence consists of positive numbers, and the numbers are 1, 4, 27, 256, and 3,125. As I said before, there are heaps of ways of writing down explicit formulas here, but perhaps arguably the most obvious one is this one. 1 is the same as 1 to the power of 1. 4 is the same as 2 to the power of 2. 27 is the same as 3 to the power of 3, and the same is true for all of these guys. And so that means that one example of a general formula for such a sequence is minus 1 to the power of k times k to the power of k. So that's just one example. One example that would answer this question for you. All right, so that's sequences of real numbers. Now we get into, now we're going to go further with sequences, and we're going to talk about sums. Okay, so to set the stage here, we're going to suppose that we have a sequence of numbers. And so one way of describing the sequence would be like this. And another way of describing the sequence is just by writing down the first few terms and then writing ... Let's suppose that we had this sequence and we actually wanted to add up all of the terms in the sequence. Or maybe we didn't want to add all of the terms up, but we just wanted to add the terms up between two specified terms. Okay, well, doing that is straightforward, but because we do it a lot in mathematics and data science, it makes sense to give it its own notation. So without loss of generality, we assume that AM is the term that occurs before AN. And in that case, adding up all of these terms between AM and AN, that's denoted with this expression here. So the way we say it is by saying the sum, so sigma, you can basically think of sigma as being what we mean by sum. So this means the sum of the AI terms from I equals M all the way up to I equals N. So I haven't done anything here. This is just a definition. If you want to add up terms in a sequence, you can denote it with this so-called sigma sum notation. All right, so that's nice. Now, this here, I want to emphasize a bit of caution here because sometimes this can be a source of confusion for students. And what this comment is seeking to address is what this letter I is actually doing here. If I tell you to add up all of the terms in the sequence between the terms AM and AN, you can do that and you don't need to know what I is. I here is just a dummy variable. It doesn't actually affect the expression at all. It's just used for convenience. Really what I mean by that is that you can replace this letter I with any other letter and the result would still be the same. If you sum up the terms AK for K between M and N, that's the same as summing up the AI terms from I equals M to N. So this is what I'm saying here. We call this a dummy variable because it doesn't actually affect the result. This is in stark contrast to the letters N and M in this particular scenario because they tell you where to start adding and where to stop adding. So I hope that makes sense there, but speak up if that doesn't make any sense. Okay. Now, awesome. Thanks, guys. Okay, now, some Mathematica. Turns out that Mathematica is quite good at doing sums, and you can get Mathematica to do some of your sums for you. So let's say I asked you to evaluate the sum from I equals 1 all the way up to 100. Actually, I won't use I, I'll use N. I'll write it over here. So since N is down here, it's our dummy variable and doesn't actually affect anything. Whereas 1 is where I start and 100 is where I stop the adding, and the answer will depend on those numbers. 1 on n squared. So let's say I've got the sequence an equals 1 on n squared, and I want to add up all those terms for n between 1 and 100. How do I do that? Well, you could do this by hand, or you could simply put this code into Mathematica here. So this is exactly this. It's just how Mathematica prefers you actually write it in. So sum, because we're summing the actual terms of the sequence, we've got to emphasize again what our dummy variable is. The reason is because sometimes you could put more than one variable in here, but you got to tell Mathematica what variable you're actually adding up in. So we've got 1 on n squared, and we're adding all of these up from n equals 1, the start, to 100, where we end. Now, unfortunately, when we do that, we get a bit of nonsense because, well, you know that when you're adding up fractions, if you want to simplify the fraction, there's a bit of work involved. And if you're adding up 100 fractions, there's lots and lots of work involved. In fact, there's so much work that Mathematica couldn't actually finish it, which is why it did finish it, but it's too large to present. And so Mathematica gives us this ... here. And so, you think that's a bit useless because I don't know what that number is. I don't even know what it's close to. So to solve that problem, you just add an artificial decimal point into your terms, and that'll force Mathematica to turn that number into a decimal that you might find a bit more tractable. So it turns out that if you add up 1 on n squared for n between 1 and 100, you get something like, so we should appreciate that this is just an approximation here, 1.63498. So that's quite nice. Okay, so if you're ever interested in adding up sums and you really don't want to do them yourselves, there's a good chance that Mathematica will be able to do it for you. Okay, now in order to help us get a bit more comfortable with what these sigma sums are doing, that we've got a question here. Let's say we've got the sequence consisting of terms of the form 2i minus 1, and we want to add this up from 1 up to n. Write this in expanded form by writing out the first 5 terms and the last term. So since we haven't actually specified n here, it's impossible to get an actual number as an answer, but we'll see what we can do here. Okay, so this is the thing we're trying to evaluate. The adding up starts at 1. Okay, when I equals 1, we've got 2 times 1 minus 1. That's just 1. The next term is 2. So that's going to be 2 times 2 minus 1. So that's just 3. And so what you see here is that this 2i minus 1, it's actually hitting all of the odd numbers between 1 and the odd number 2n minus 1. So remember, since n is the last thing we add up, if we chuck that into that, we'll end up with that. So the point of this question was really to get you comfortable with what's actually going on with sums. What are we doing? Adding up the numbers between the specified start and ending points. Okay, now the next question is to ask you to do this process in reverse. Now we've got a sum expressed using this notation where we specify what the first few terms are. Then we've got a dot, 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 and then we've got a 1 on n times n plus 1. Now, you always have to be cautious when you see this dot, 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 because technically speaking, anything could be in there. But in this case, we're sort of asked to use our intuition, use the pattern that's hopefully the most obvious to work out what this is. Okay. So it looks like you may notice that basically all the terms here, at least the ones that are written, are of the form 1 divided by some number times the next number along. So that original number plus 1. So if we let that number be I, then all of these terms look like 1 on I times I plus 1. Okay, so remember, this is just our dummy variable. In order to give it meaning, we have to specify where it starts and where it stops. Well, the first term is 1 on 1 plus 2. So it looks like I starts at 1 and it goes all the way to n here. All right. So how would we put this as a sum? Well, this is the answer here. Because remember, what is this saying in words? This is the sum from I equals 1 up to n of the terms 1 divided by I times I plus 1. So this is how you would convert that into sigma sum notation. So I hope that's all clear. Okay. Now, let's have a look at some more sums. Okay, so we're looking at adding up terms. The terms in the sequence we're dealing with are I squared, and we're interested in summing these up from I equals 1 to n. Now, you can actually prove using mathematical induction. I think this is a technique that you will have encountered earlier. You can prove using mathematical induction that this formula is true. It basically says that if you add up all of the squares between 1 and n, so you're adding up all the squares between 1 squared and n squared, then that result happens to be this fun formula here, n times n plus 1 times 2n plus 1 divided by 6. Now, I won't prove this. In fact, it might be a fun exercise for you guys to try yourself. But the point of this is to see what happens the point of this question is to use this expression here to find another expression for this guy here. What if instead of going up to n, we went all the way to n plus 1? What then? Well, this is more or less just an exercise in being familiar with formulas. Since this is true for each n we think of, it's also going to be true for n plus 1, because, if it's true for every integer n, then it's true for every number of the form an integer plus 1, because that is another integer. Okay, so all we're going to do is replace every single n we see with n plus 1 and see what we end up with. Okay. That's a bit messy. So the first n plus 1 goes there. This n becomes an n plus 1. This n becomes an n plus 1. This n here also becomes an n plus 1. We've just got that 2 out the front. So this is the actual answer here. But of course, it's good manners to simplify things as much as you can. And once we expand and simplify and factorize it, we don't need to expand. We just need to play with this term and this term. And what we end up with is that n plus 1 times n plus 2 on 2n plus 3 on 6. So that was a fun little exercise there. Okay, the next thing we're going to do with sequences. We've just been adding them up. Now we're going to multiply them all together. So this time, the notation is almost exactly the same, instead of this sigma, we now have this big pi thing. P for product, I suppose. So if you've got a sequence and you just want to multiply all of the elements of this sequence between k equals m and n, then that can be expressed using this notation here. And of course, the result is what you'd expect, am times am plus 1, and you keep doing that until you get to an. So technically speaking, this only makes sense if n is strictly bigger than m. If it's the other way around, well, then you just reverse the roles of m and n in this formula. All right. Now, something that comes up quite frequently when we're dealing with products is this idea of factorials. So let's say you've got a positive integer n. Mathematicians quite like talking about this number n factorial. And no, that doesn't just mean, so there's an exclamation mark here. It doesn't mean that we're really excited about this number n. Rather, it means a new mathematical concept, the idea of factorial. So when you see this n exclamation mark thing, that means n factorial. What does that mean? It's the product of all positive integers up to and including n. So if it's an integer, you go n. If it's a positive integer, you go n times n minus 1 times n minus 2, and then all the way down to 1. In the product notation that we were just dealing with, this would be the product. Didn't leave enough space there. This would be the product from k equals 1 up to n of just these numbers k here. So this product comes up so much that we prefer to not use the product notation and instead prefer to use this exclamation mark notation here. All right. So what's coming next? Oh, yes. So just some questions to get you familiar. Oh, sorry. Before we get into that, I said that this n factorial was defined for positive integers n, but for various reasons that we might not come to in this course, it turns out to be useful to define 0 factorial as well. And you might think, with this definition, it doesn't make sense. It doesn't make sense to take 0 factorial because there are no integers between 0 and 1. And yeah, that's right. So we just say by convention, 0 factorial is 1. There are reasons for that, but I might not go into that now. Okay, I might just do this question before we go for a 10-minute break. So my question here is, I've got some expressions involving factorials and products. Need you to simplify these as much as you can. Okay, well, let's have a look at the first one. So this first one, in words, remember, what are we saying here? This is the product of the terms 2 to the j from j equals 2 to 5. So that means we're multiplying things together. What are we multiplying? We're multiplying these two j terms. We start with 2 to the 2 and go all the way up to 2 to the 5. So in between, we've got 2 to the 3 and 2 to the 4. Using our index laws, we go 2 plus 3 plus 4 plus 5. That's equal to 14. 2 to the power of 14. I didn't do this by hand. I trusted a computer to do this for me. The answer is 16,384. So that's the first one. Hopefully nothing too unnerving there. Next one, 10 factorial divided by 8 factorial times 2 factorial. What's going on here? Remember, factorial is 10 times 9 times 8 times 7 all the way down to 1. 8 factorial is 8 times 7 times 6 all the way down to 1. And 2 factorial is just 2 times 1. Now you may notice that we get a lot of cancellation here. 8, 8, 7, 7, 2, 1, 2, 1. So what we're left with is just 10 times 9 divided by 2 times 1. And the answer to that is 45. And finally, let's have a look at this, n plus 2 factorial. So that's the product of all integers between n plus 2 and 1. So that's n plus 2 times n plus 1 times n all the way down to 1. And then on the bottom, n factorial, n times n minus 1 all the way down to 1. We again get heaps of cancellation here. What we're left with is n plus 2 times n plus 1. Okay, I think I'll leave it there for a 10-minute break. I think I need to get a drink of water. So I'll leave you to it. If you have questions, just put them down there and I'll hopefully address it when we all reconvene in a couple of minutes. All right, thanks guys. I'll see you shortly. All right, hello again, everyone. Xiaowang, did you want to, if you're here, did you want to elaborate on what you meant by 45 and n plus 2 times n plus 1? Was that an answer to a particular question I asked? All right, never mind. Let's keep going. Oh, sorry, I got an answer. Okay, cool. All right. Okay, so you may recall that we just finished talking about sequences. We've been talking about sums in sequences, and we've also been talking about products of sequences. We're now going to talk about recursion relations. So the name of the game here is still sequences as before, except this time we're being a bit more tricky about how we're describing them. So if you can write each term explicitly in terms of k, then that means you have a general formula. But if instead, if instead you can write down all of the sequences explicitly in terms of the sequences, in terms of the terms of the sequence that have come before, when that happens, we say you have a recursive sequence or a recursively described sequence. And the explicit formula which tells you how to write, how to describe these terms, that's described as a recursion relation. Okay, so that probably all seems a bit abstract at this point. So let me give you an example to describe what I mean by this. Okay. So consider the recursively defined sequence AK. K is running from 1 up to infinity. The first term of the sequence is A1 equals 2. This is the only term that's given explicitly. For any other k, well, for any k bigger than 1, we say that the next term along in the sequence, AK plus 1, that's defined to be 1 divided by 3 minus AK, which was the last term. So here we've explicitly described how to jump from the last term in the sequence to the next term in the sequence. So since we've been able to do this explicitly, we say that this is a recursive formula. Okay, well, what does this sequence actually look like? Well, we were told that the first term in the sequence was 2, but what about the next one? Well, the second term in the sequence is a of 1 plus 1, and our formula tells us that this can be done by going 1 divided by 3 minus A1. Remember, we were told originally that the first term of the sequence was 2. So that means that the answer is 1. We can play the same sort of game with the next term in the sequence. A3 is equal to 1 divided by 3 minus the last term in the sequence, A2. And of course, this is equal to 1 divided by 3 minus 1, which is exactly a half. And we can continue doing this to work out what all of the elements in the sequence are. So that's pretty nice. So that's an example of a recursively defined sequence. Now, some of you may have come across the Fibonacci sequence in earlier mathematics courses. This is an example of a sequence of numbers, sequence of integers, in fact, that are defined recursively. So in the Fibonacci sequence, you specify that the first term in the sequence is 1, you specify that the second term in the sequence is 2, and you specify that for any other term in the sequence, can be found by simply adding up the last 2 terms in the sequence. So the kth term can be found by adding up the k minus 1th term to the k minus 2th term. And so we can actually use this to work out what the sequence is. F1 is equal to 1, F2 is equal to 3, F3 is given by the sum of the previous two terms, which is 2. F4 is given by the sum of the previous two terms, that's 2 plus 1, that's equal to 3, and we can keep doing this. Now you might think, well, maybe that's a bit useless. I mean, because we aren't told explicitly. The only way to work out explicitly what a given term in the sequence is by working out what all of the terms in the sequence are that went before that particular one. Question here, Fibonacci sequence question mark. Could you elaborate on that at all? Anyway, so yes, this was actually yes, this is exactly the Fibonacci sequence as I outlined there. So yes, the third term in the sequence is just F1 plus F2, and the fourth, which is 2, and the fourth term is F3 plus F2, which is 3. So yes, this is the Fibonacci sequence. What I think is extremely interesting about the Fibonacci sequence is that even though it is defined recursively, you can actually turn this recursive formula into an explicit formula of the kinds that we've already seen. There is actually a general formula for the Fibonacci sequence here. And it involves numbers that you wouldn't think actually come up, because all of these are whole numbers, and yet the explicit formula for this involves a number which is very much not an integer. In fact, it's not even rational. It involves this root 5 thing. You may have actually seen this number before. 1 plus root 5 on 2 is actually called the golden ratio. You may have heard of this before. The reason it's such an important number, well, one of the reasons it's an important number is because it comes up in describing this particular sequence here, but it has some other fun applications as well. You may want to look up the golden ratio on Wikipedia and see if there are any applications there that tickle your fancy. Okay, so that was the Fibonacci sequence. Now you may be wondering, well, how can you verify this is true? And again, this is actually something that can be proven using mathematical induction. In fact, I would suggest that this is something that you could all try yourself. I won't go into it. This might be a fun exercise for you to try yourself. I can promise you it is just elementary techniques along the lines of techniques that you already know. Now, that verifies that the formula is true. Of course, there is a question before that. Where does this formula come from? You know, if you're given a formula that's correct, you should be able to prove that it's correct. But how did I know that 1 plus root 5 on 2 to the power of k is the correct number here? Well, unfortunately, the answer to that, it's slightly beyond the scope of this course. But if you're extremely interested, maybe you could come to my office hours and we can talk about where this comes from. But yes, slightly beyond the scope of this course, I would suggest. Okay, now we're wrapping up. I think we're close to wrapping up subsection 5.1. So I want to sort of summarize what we've seen so far in terms of sequences. Namely, that we've seen a few different ways of actually writing these sequences. The first one, I think, is sort of the naive approach to writing sequences. This basically boils down to, writing down the first few terms of a sequence and hoping, I put in quotation marks there, hoping that the reader finds it obvious what you actually mean by that. Now, for example, you could write 3, 5, 7 as the first 3 terms of a sequence and then write ... indicating that you can't be bothered to explain what's coming next. most of the time this approach would be reasonable, but you do have to be quite careful sometimes because, well, to me at least, there are two obvious ways of continuing this sequence. You could just be 3, 5, 7, 9, 11, and so on, and your sequence would be all of the odd integers, odd and positive integers. But there is actually another way of continuing this sequence. You could have 3, 5, 7, and then jump straight to 11, 13, skip 15, go to 17. What's going on here? This would be all of the prime numbers starting at 3. So I would urge caution whenever you write a sequence in this way. Make sure it is actually obvious what's going on here, because sometimes it is ambiguous. Okay, so that was perhaps the naive way of describing it. A much better way of describing a sequence is if you happen to be fortunate enough to actually have the sequence described explicitly, i.e. your sequence is such that each term can be written explicitly with a single formula involving n itself. So that's very nice when that happens. But sometimes, unfortunately, most of the sequences you deal with in real life, I think, are actually presented with this form, where you're only given the first few terms in the sequence, and the rest of the terms can only be described recursively in terms of previous terms in the sequence. So when you do this, you specify the first few terms and then say that any other arbitrary term can be written explicitly in terms of the terms that have come before it. Now, this is all nice. Sometimes you can actually jump between these. So we've actually seen a lot of examples. So for example, with the Fibonacci sequence that we just did, we started with something here and we jumped back to here using that golden ratio. Now, sometimes, well, let's do a bit more playing with our recursively defined sequences. Let's say we've got a sequence of numbers. We've described the first two explicitly, and I'm asking you to work out the next 3 terms in the sequence, and the sequence is defined recursively. So I won't say this out loud, but we've got this formula here, which hopefully describes to us how to actually calculate these numbers. All right, let's get to it. C2. According to this formula, C2 is equal to 2 minus 1 times the term that came immediately prior, CK minus 1, then plus 2 times the term that came 2 steps prior, plus the K itself. So in this case, we actually know what C1 and C0 is. So C1, we were told, is equal to 2. So 2 minus 1 times 2 is 2, plus 2 times 1 is just 2, plus 2, that all adds up to 6. Okay, what about the next one? Well, in the same game, K minus 1 goes there. The term immediately prior was C2, which we now know, plus 3 times C1, plus 3. We can add that up to get 21. And finally, this last computation ends up giving us 91. So of course, we could keep going as far as we want, but we won't because hopefully the point is being made now. Okay. Bit more practice here. This time I'm giving you a recursive relation here, but I'm not actually saying what the initial 2 numbers are. So this formula here describes the sequence explicitly in terms of the 2 numbers that came before. And so in order to work out what this sequence is exactly, you would have to specify B0 and B1. But I'm not going to do that because the point of this question is to find expressions for BI plus 1 and BI plus 2. This is quite similar to the question we dealt with a while ago, where you had a sum from I equals 1 to n, and you had to use it to find an expression for the sum from 1 to n plus 1. All right, it's more or less the same sort of strategy. Since this happens to hold for all I greater than or equal to 2, if you simply replace every instance of I with I plus 1, you'll get a formula for bi plus 1. So bi becomes bi plus 1. 5bi minus 1 becomes 5b I gets replaced with I plus 1 minus 1. And this becomes minus 6bi plus 1 and then minus 2 here. But of course, you can cancel the plus and minus 1 there, and you can simplify the 1 minus 2 to get this expression here. You can, of course, do the exact same thing for I plus 2 as well. So what this is more or less reflective of is the fact that the general purpose of this sequence is to work out what happens to one particular term if you know what the previous two terms were. And you can do that no matter how far along in the sequence you are, as long as you know what came before it. All right. Now, I told you previously that you could sometimes jump between various ways of presenting sequences. Now, I want to take a sequence for which we actually have a general formula and turn it into a recursively defined sequence. So my sequence of numbers, it's an with n running from 0 to infinity, and each term an is given by 5 times 2 to the power of n. Show that, despite the fact that we've got this term written explicitly, show that you can write it recursively, and namely that the recursive relation is this one here. In words, what this is saying is that our sequence starts at 5, and that for any other term in the sequence, to work out what any other term in the sequence is, you simply need to multiply the last one by 2. All right. Well, I mean, clearly that's true. If we've got a sequence that satisfies this, you just have to plug in n equals 0 to find that this is true. Just as a courtesy, I included the second term in the sequence as well. But what happens generally? How can I show that this is true for any n greater than or equal to 1? How can I show that that's true? Well, playing with the numbers, essentially, I want to prove that this left-hand side equals this right-hand side. So I'm going to start with the left-hand side and manipulate it until hopefully I get the right-hand side. Well, an. The only information that we have to work with about an is that the actual definition of the sequence. An equals 5 times 2 to the n. So I just write it there. Now I keep in mind that I need to manipulate this so I get a to the n minus 1 there. I do that just by pulling a 2 out. So using my index laws, this 5 stays there, but I'm going to pull this 2 out. So if I pull a 2 out of 2 to the n, I'm left with 2 to the n minus 1. Now, what is so great is that this is exactly equal to the n minus 1 term in this sequence. So what I end up with is 2 times an minus 1, and I find that indeed this sequence can be defined recursively by simply taking any term in the sequence and multiplying it by 2 to get the next one. Okay, now I think our last example before moving on to 5.2 are the Catalan numbers. Now this, I did find this a bit tricky when I first looked at it. So we've got a sequence of numbers, the terms are called Cn, and they're defined by taking 1 divided by n plus 1 and multiplying it by 2n choose n. If you're unfamiliar with this notation, This comes up in probability when you're trying to work out how you can select X number of things from a group of Y. The actual definition of, in case you're unaware, the definition of X choose Y is X factorial divided by Y factorial times X minus Y factorial. So yes, this sort of bracket 2n on top, n on bottom, that means the number on top, choose the number on bottom, and this is mathematically what that means. It's written in terms of the factorials that I just described. Oh, sorry, I should have left that. And choose n x minus y factorial. Okay, so the question, we've got this sequence of numbers. We know we've got a general formula for them. They're written explicitly. I want to show that there's actually a recursion relation going on here. Show that each term in the sequence, the CK term, can be constructed by taking the previous term and multiplying it by 4k minus 2 divided by k plus 1. Now, don't worry if you don't follow this. I think this might be, I suspect this probably is the trickiest proof we encounter this evening. But let's get on with it. Okay, so, well, the actual question asks us to just work out what the first three ones are. So how do we do that? Well, C1, by definition, 1 divided by n plus 1, n is 1, times 2n, n is 1, 2 choose 1. So that's 1 on 2 times, remember how our 2 choose 1 looks like. 2 factorial goes on top, 1 factorial goes on the bottom, and 2 minus 1 factorial also goes on the bottom. But of course, if you simplify that, you'll just end up with 1. So that's nice. Proceeding in this fashion, we can calculate C2. So I might just do this one quickly. 1 divided by 2 plus 1 times 2n is 4 now. 2 choose 2. So this is equal to 1/3. Remember how 4 choose 2 is defined. It's defined to be 4 factorial divided by 2 factorial times 4 minus 2 factorial. So that ends up being that guy there, and that's just equal to 2. And C3, we can continue on this fraction to find that C3 is equal to 5. Now for what I consider to be the very tricky part, where on earth does this formula come from? Well, we'll just use the same approach as last time. Start with the left-hand side, hopefully manipulate it to the extent that I can get the right-hand side popping out. So left-hand side, Cn. Now, by definition, remember, this is 1 on n plus 1 times 2n, choose n. Remember, that's 2n factorial divided by n factorial times n factorial. Okay, so that's just the definition. Now I need to do some manipulating. Okay, I want to manipulate it so that the ck minus 1 appears. Well, ck minus 1, that involves, let me just write it here. Ck minus 1 is 1 divided by, I've sneakily swapped my k's and n's here, but of course we remember that this is a dummy variable and doesn't actually matter. 1 divided by k times, now if k, if n is k minus 1, what we'll end up with is 2 times k minus 1, and we're taking the factorial of all of that, and then we divide by k minus 1 factorial and then times another k minus 1 factorial. Okay, so somehow I need to pull all of that out from this expression here. Well, 2n factorial, remember that's just 2n times 2n minus 1 times all of the other integers between 2n minus 2 and 1. But that number is exactly that one there. So that's as far as we'll play with the numerator. The denominator, on the other hand, we need these n minus 1 factorials on the bottom. We can get this here, and we have 2 copies of n popping out, and this n minus 1 goes over there. So it is looking like a bit of a mess now, but this is actually what we want, because this term is exactly cn minus 1. So now all we need to do is manipulate this term so that it looks like that. Well, 2n times 2n minus 1, that's 4, sorry. That's 4n squared minus 2n, but that cancels with this n on the bottom here. And yes, we end up with exactly what we want. It's just that we did it in terms of n instead of k. So yes, that was a bit involved. You might want to review that later or perhaps not. But this is just illustrating the power of how good it is if you've got an explicitly defined sequence, and maybe sometimes it's useful to turn that into a recursion relation. All right, so I believe that takes us to the end of 5.1. I'll leave a brief amount of time for questions now. If there was anything that's unclear, speak up and I'll do my best to address it. All right, I'll take the silence as confirmation that I should keep going. All right, now limits. This is where we really get into the calculus side of things. And this, I consider limits to basically be the main driver for the need to consider sequences at all. Because, well, limits of sequence concern behavior of sequences with infinitely many terms when you're really, really far away from the start. If your sequence only has finitely many terms, somehow that's easier to deal with. But if you've got a sequence with infinitely many terms, trying to work out what's going on really, really far from the start, that becomes a bit of a challenge. And in order to get a good theory about the behavior of sequences close to, well, far away from the start, you need a good language to treat that. The correct language to use when we're talking about sequences with infinitely many terms is the limit. You might be scared by limits. They are typically quite difficult to understand, but hopefully I'll be able to give you a good idea about what's actually going on with limits. Okay, the setting. We've got a sequence, as I said, with infinitely many terms. Let's just call that sequence AN, and the terms are running from n equals 0 to infinity. We could start at 1, we could start at 2, we could start at any finite number, but we do need to end at infinity. Okay. Now, we say that this sequence converges to the number L if, what I'm about to say is a bit loosey-goosey, but hopefully gives you the general impression. This sequence converges to the number L if you can make these AN terms arbitrarily close to L by going far enough along in the sequence, i.e. by making n arbitrarily large. So this is where this whole sort of accuracy thing comes into play. I want my sequence to be arbitrarily accurate. I might not be able to make my sequence exactly what the answer I want is, but I might be able to get arbitrarily close by going arbitrarily far along in the sequence. So this is the rough idea of what we're trying to capture here. Now, I know that this is a very abstract definition. Hopefully, we'll go through some examples that make this idea a bit clearer. Now, if you're really interested, maybe this just goes straight over your head, but this idea of arbitrary precision and arbitrary accuracy by going far enough along, the way to describe this correctly and formally is with this sentence here. We say that the sequence converges to L if, no matter what epsilon bigger than 0 I pick, you can find an n, that's a natural number, so that your sequence is actually close to that limit, close as in epsilon close to that limit, provided you are actually far enough along in the sequence. So let me try and explain what all these terms here are. Epsilon, we think of epsilon as a level of accuracy. Since I want to get, even though I might not be able to get accuracy to 0%, I might be able to get accuracy to 0.1%. I might be able to get accuracy to 0.01%. No matter what level of accuracy I pick, I should be able to force my sequence to be that accurate, at least by going far enough along in the sequence. So how does this play out? Well, let's have a look at this sequence here. I shamelessly ripped this particular image from Wikipedia because I find Wikipedia to be a very good source for mathematics. I'm looking at the sequence n plus 1 divided by 2n squared. Now, you may have a look at this sequence and say, well, it looks like all of these terms here, they're getting pretty small. In fact, you might be even willing to claim that n plus 1 on 2n squared converges to 0. Not A, it converges to 0. Now, how do I know that? Well, to give some idea, we can try use this epsilon n definition. If I pick any epsilon I think of, I should be able to force my entire sequence to be like within that epsilon neighborhood by going far enough along in the sequence. All right, let's choose epsilon to be 0.6. Well, the good news is I can actually force my entire sequence to be in this range. However, I have to get rid of the first term in the sequence, but that's okay. I'm allowed to tuck away the first few terms of the sequence, and the rest of it should be within that threshold. Okay, well, that was 0.6. What about another number? Can I force my entire sequence to be within 0.2? Well, if we draw 0.2 here, yes, I can actually force my entire sequence to be within this range, except this time I have to chuck away the first 3 terms. But that's okay, because basically all of the sequence except for the first few terms are actually within that. Now, you may notice that no matter what epsilon I pick, I'll be able to do this. Of course, by making epsilon really, really small, I have to chuck away more and more terms, but there'll always be a cutoff point beyond which everything in the sequence is as close to my limit as I want. So that's the idea of a limit of a sequence. I can appreciate that this is a very abstract definition and may not mean much to you. So now, hopefully, now the aim is to look at some more examples of limits in sequences, and hopefully that'll help your understanding here. Okay. Now, before we get into examples, it turns out that just a bit more notation is useful. In the situation where we do have a sequence that does actually converge to a number L, L is said to be the limit of this sequence, and that's written with this notation here. L equals lim n arrow infinity an. So this is written L. If you were to say this equation in words, what you would say is L is the limit of an as n tends to or goes to infinity. So you write it like this, but you say it like this. Now, sometimes sequences don't have limits. If the limit does not exist, we say that the sequence is divergent. But if the limit does exist, we call the sequence convergent. Okay, so those are some conventions. I think now we're going to be getting into some actual examples of sequences. So that's nice. Okay. Question. I'm giving you two sequences here. The first one, I'm describing exactly. An is just 1 divided by n. That's easy enough. Okay. Now my second sequence I'm actually giving to you recursively. I'm describing the first term in the sequence, and I'm telling you how to hit any other term in the sequence, provided you already know what the last term in the sequence was. Are these sequences convergent? Are they divergent? What is their limit? All right. Now, the first one. Actually, I'll make this an opportunity for some participation. I've got two sequences here, AN and BN. If you feel up to it, maybe you could write in the chat describing which of these sequences converge and what they converge to. Excellent point. So yeah, so n is greater than or equal to 1 here. So yes, AN converges to 0. Yep, we've got some more converging to 0. AN converges to 0. So yes, I guess we've more or less concluded that AN converges to 0. And there is a way to prove this rigorously using the rigorous definition I gave you. But roughly speaking, this 1 divided by n, since n is getting large, arbitrarily large in fact, 1 divided by n is getting arbitrarily small. Since it's becoming arbitrarily small by having n arbitrarily large, the limit does exist, and it's going to be 0, and the sequence is convergent. So that perhaps is the easier of the two. What about Bn? This is slightly tricky because I haven't given you the sequence exactly. I've only described it recursively. What do you think Bn is converging to? Or does it converge at all? Maybe it doesn't converge. What do you think? We've got a 0. Another 0. Yes, good job, guys. You're definitely on the ball here. So what we think here is that even though I don't know what the sequence is explicitly, I know that each time I'm halving what just came before. If I halve a number, that always brings it closer to 0. And so if I keep halving it, I'm going to get closer and closer to 0. And so therefore, I should converge to 0. Perhaps the easiest way of seeing this is by noticing that even though it's described to me recursively, I can actually make this into an explicitly defined sequence. The terms are Bn. The Bn terms are given by minus 1 divided by 2 to the power of n. If I raise 2 to the n, with n getting large, that's getting very, very large. So this whole thing is becoming quite small. So that means the limit is 0, and therefore the sequence is convergent. All right, awesome. Now for some tricky ones. Let's start with Cn. So n is bigger than 1 here, and n will be bigger than 1 here. Does Cn converge? If so, what does it converge to? I think this one is slightly tricky. Divergent. Yep. Okay. Very good. Clearly, you all know your stuff. Yes. So this sequence is divergent. Why is that? Well, if we just look at what these terms are, -1 to the n, as we've discussed earlier this evening, -1 to the n is actually going to be 1 or -1. It depends entirely on whether the n number is odd or even. So it bounces between -1 and 1. So we can think of that as, just going 1, -1, 0. It sort of bounces between -1. Now, this sequence does get arbitrarily close to both 1 and -1. In fact, it actually equals 1 and -1 for many of the terms. Now, while the terms do get arbitrarily close, the sequence, I guess the reason this sequence is distinguished from the other sequences which we know are divergent, that we know are convergent, is because just getting arbitrarily close is not enough. You actually have to get and stay arbitrarily close. Of course, the sequence gets arbitrarily close to 1 and -1 all the time, but it doesn't stay arbitrarily close to either of them. So that is the reason we say the sequence is divergent. And yes, basically, I would say that this reasoning is exactly described from Zhao Wang in the chat. Two parallel lines can't converge. And yes, that is more or less what's going on here. Okay, now the final tricky one. What about Dn? So R is some real number. We're raising that real number to the power of n and looking at the corresponding sequence. So yes, if you could answer that. So yes, we've got yes, good, depending on R's range. We've also got a question from Trove about the previous one, asking whether or not the sequence looks like that. I would say yes and no. Technically speaking, the sequence is only defined for natural numbers. So if you were to graph this, there wouldn't really be a reason why you should join these dots up. I mean, it could if you think it would help, but technically speaking, those straight lines aren't really described. So yes, we've got an answer here. It's convergent if R is less than 1 and divergent if it's bigger than 1. That's almost correct. Why do I say it's almost correct? Because I said R is a fixed real number. I didn't say it was positive. So the correct way to describe it is really in terms of the absolute values. And of course, the other question is, it depends on whether it will get different behavior if R is 1 or -1. So let's split it up into cases. We noted before that if we kept multiplying a number by a half, it would shrink. The reason that happens is because the absolute value of that is less than 1. So if R is less than 1 in absolute value, then what we're doing is continually multiplying these numbers to each other. They shrink, and we find that the limit is 0. Now, what happens if R is exactly equal to 1? Well, 1 to the power of any number is just 1. So this sequence is just flat. Every term of this sequence is 1. So therefore, the sequence gets and stays arbitrarily close to 1. So therefore, the limit is 1. If R is -1, then we get this 1 -1, 1 -1 thing that we've already seen. And we know that that's divergent. And finally, if the absolute value is bigger than 1, then the size of each of these terms is growing each time we move along in the sequence, so it doesn't converge. So yes, that's an idea of sequences and limits there. Okay. I think now might be a good time to have actually no, I'll invite questions during the break, but I'll keep powering through for the moment. So we've done some examples of limits. Now, limits are a very, very important thing in mathematics and in calculus. And there are lots of rules that come up for limits that are very useful. And so we're going to have a look at some of those rules now. It's convenient to describe this in terms of a theorem, I think. So the theorem concerns what happens if you take two sequences that you know are convergent. Let's say they converge to L and M respectively. And we're interested in combining these sequences in interesting ways. And we're interested to see what happens to the resulting limits. Okay, so I've got two sequences and we've just got some number C, that's a real number. Then if these original sequences were convergent and we add them up or take their differences to find a new sequence, then that new sequence also converges and the limit is just the sum or the differences of the previous, of the original sequences. So that makes sense, I suppose. On the other hand, if we take one of the sequences and simply scale every term of that sequence by the same number C, and we look at the new sequence, then that sequence also converges, and the limit is C times L, where L was the original limit. A slight generalization of this is what happens if you take these two convergent sequences and multiply them together. Well, then again, the resulting sequence is also convergent and it converges to the product of limits. So the way that you would say this one, a colloquial way of describing this is by saying the limit of the sum is the sum of the limits. So this is a fun way of describing that. And of course, this one can basically be described in the exact same way. The limit over the product of sequences is the product of the corresponding limits. Now, there is a version of this which holds for division as well, but it only works if what the denominator is converging to is not 0. So that's pretty nice. And now I want to, maybe I'll leave with this discussion here in the last 2 minutes before our next break. I'll explain what the issue with dividing by 0 is. And I've noted a typo here. Okay. Now, my claim is that if you're looking at two convergent sequences, you're taking the ratio of these two, and the bottom one is converging to 0, then really all bets are off as to what's going on here. So let's have a look. For an example, let's take my denominator sequence to be 1 on n squared, and let's take my numerator sequence to be 1 on n. Then if I take the numerator divided by the denominator, well, 1 on n divided by 1 on n squared is exactly equal to n. N is divergent because that number n is getting arbitrarily large. It's not converging to any real number. So that sucks. But I can actually make this sequence converge by looking at a different example. So for example, if I chose an to be 1 on n squared and chose bn to be the same thing, then the ratio is of course 1. So now the limit of this sequence is 1. So whenever you're going to use this theorem, always be careful and make sure that your denominator does not go to 0. Because if it does go to 0, you're going to have to do a bit more work in order to determine what's actually happening there. Okay, I think I'll leave it there for the moment. Thanks for your attention. I'll get back to you in about 10 minutes. If you have questions on what's been covered so far, put your questions in the chat and I'll hope to address it when I get back. All right, sweet. Enjoy your break. Hello again. Right, so we'll make a start with the final leg for this evening. Thanks to those of you who have managed to stick it out this far. All right, so just before we had our break, we were quickly looking at a theorem which describes how you can use information about the convergence of two sequences to make conclusions about the convergence of combinations of those sequences. Most of them were basically as you'd expect. The only subtlety, I guess, is when you're dividing your sequences, this rule for limit ratios only holds if the denominator is non-zero. Essentially, the reason is that, well, it's the usual divide by zero issue in that you can't do it, and that makes studying limits quite difficult as well. All right, so now on to another theorem. This is a pretty fun theorem. This is called the Squeeze Theorem. Now, like the other theorem that we had, this theorem is about concluding convergence of a particular sequence if you already know that two of the other sequences are convergent. So the name squeeze basically comes down to this inequality here. If your three sequences are so that this sequence is sandwiched between the other two sequences, or at least that statement is true if you're far enough along in the sequence, and if it so happens that both of these outer sequences converge to the same number L, then the same is true for the sequence that lies in the middle. Now, this is a fairly natural theorem here, and perhaps the cleanest way to demonstrate why it's true is by, well, looking at an example. The favorite example that commonly comes up in calculus textbooks is this sequence here. Now, we've got to be a bit careful. This AN is not the same as this sequence up here. This is the sequence that we're trying to determine convergence of. Now, how might we go about determining whether this sequence converges or not? Well, sine of n, I guess that we know that's a periodic function, and in particular, we know that no matter what you put inside n, the result is always going to be between -1 and 1. So that means that when you divide the results by n, you find that the sequence lies beneath 1 on n and lies above -1 on n. Now, what's so great is that we know that both of these outer sequences are actually convergent. We did that a couple of examples ago. 1 on n converges to 0, and the same is true for -1 on n because of that limit theorem that we had a while back. Both the outer sequences converge to 0, so that means the inner sequence converges to 0 as well. And this is best done with this glorious picture here. Now, I think this is I've got to be a bit careful here, because technically what's being graphed here are functions, but we're actually interested in the sequence. And so that means that as opposed to the function, we're only interested in the sequence at, discrete points here. But if we ignore that subtlety there, what's going on here is we've got this curve here, remembering that our sequence is actually just a collection of points on this curve. We want to see if it converges or not. Well, Well, we've got things to work with here. We've got this 1 on x function, and we've got this minus 1 on x function. And if I can draw this correctly, you may notice that these two outside functions actually contain the thing that we're most interested in. And since both of these outer functions are converging to 0, that means the same is true for what's going on the inside. This is why it's called the squeeze theorem, because the outside limits are actually squeezing the inner one into the value that it's supposed to be going to. So yes, that's the good example of the squeeze theorem there. Okay, we're going to continue our look into sequences now with some more fun examples. Here, I'm providing a list of some well-known limits. So these are limits that you should be able to recall, or sorry, not recall, but if you're required to in assignments or exams and it doesn't require you to prove it, these are basically limits that you should be able to take for granted. So the first one is, if we've got a constant c, and we're looking at the sequence where we raise that number c to the power of n, and we take the limit, well, this is actually something we saw a couple of examples ago. The limit is going to be 0 if the absolute value of c is less than 1. If c is exactly equal to 1, then the limit is 1. But if c is any other real number, then we know that the sequence is divergent. So this is what we've already seen. This is another, this is an interesting one. We're now looking at a positive c, and instead of raising it to the power of n, we're raising it to the power of 1 on n. So what's going on here? Well, we know that if we raise any number to the power of 0, if we raise any positive number to the power of 0, the result is always going to be 1. And this statement here is essentially the limit version of that. If you take a number and raise it to the power of a number which is almost 0, then the result is almost going to be 1. So we say that concretely by saying that the limit of c to the power of 1 on n, that is 1 as n goes to infinity, because the numbers we're raising c to are getting increasingly small, because we know that 1 on n gets pretty small as n goes to infinity. Okay. Another fun example. This time we fix a positive number r, and this time our sequence is found by taking 1 on n and raising that to the power of r. Now, we know that 1 on n goes to 0 as n goes to infinity, but in fact the same is true if you raise n to the power of any fixed positive number, because no matter what positive r you pick, this denominator is still getting very large as n goes to infinity, so 1 divided by that is getting quite small. Okay, now this I think is a very, very interesting one, because it's somehow a combination of these previous two ones. What's going on here? We're taking a number n and we're raising it to the power of 1 divided by n, and that's our sequence, and we're taking n to infinity. Now, there are some competing there are some forces here that you think might be competing, because, you know, if we just look at n to the power of some number, then this gets large as n goes to infinity. But on the other hand, if we just take some number and raise it to the power of n, this is going to 1 as n goes to infinity. And somehow both of these impacts are here. We're raising a large number to the power of something that's close to 0. In this case, it turns out that this behavior wins. The 1 on n is much more powerful than the n in the, the 1 on n in the index here is much more powerful than this n here. And so in the end, because it wins, we end up going to 1 here. Now, this one I think is straightforward, n factorial. As n goes to infinity, n factorial is definitely going to infinity. So 1 divided by that is certainly going to be going to 0. Another one here. So we've got some competition here again. We're raising a constant c to the power of n, but then we're dividing it by n factorial. Both the top and the bottom are getting pretty large, but it turns out that the bottom is getting bigger much faster than the top is, and so this particular limit is 0. So not entirely trivial to see why that's true, but it is true. Now this, I think, is definitely the most exciting limit here. 1 plus 1 on n to the power of n. Now what's going on here? Well, similarly to what we've seen before, if we take a number and raise it to the power of n, and I'll write it down here. If we take some number, some fixed number, and raise it to the power of n, this goes to infinity as n goes to infinity. But on the other hand, if we look at 1 plus 1 on n and raise it to just some number, this actually goes to 1 as n goes to infinity, because we're raising a number which is really, really close to 1 to some number. And if this number here is close to 1, then it should still be close to 1 when you raise it to the power of some other fixed number. But we've got both of these behaviors competing with each other here, and in the end, there's this beautiful balance here, because when the limit is not 1 and it's not infinity either, rather it's this really special number e, which is known as Euler's number. So that's where e comes from. And there is a slightly more general version of this. If instead of this limit here, you replace this 1 with just an a, then you end up with e to the power of a. So that's Euler's number there. That's quite exciting. So yes, are there any questions at this stage? All right, I'll keep moving on. Now, no, yes, just remember them. Yes, would be good to remember them if you can. Hopefully there'll be some opportunities to practice these and you might be able to remember them. All right, now we get into some really fun stuff. We combine the sigma sum notation that we were doing before with infinite sequences and limits. If we combine these techniques together, what we end up with is the idea of the infinite sum. So this is a bit of a thing to get your head around. Basically, the idea is you take an infinite sequence and just add up all of the terms, even though there are infinitely many things to add up. Of course, what I just said doesn't really make sense. So what we're trying to do here is make sense of that. So if we've got a sequence, we define a new sequence, which is basically adding up the first few terms of this sequence. So the series of AI is a new sequence Sn, n is running from 1 to infinity, and Sn is defined to be the sum of the original sequence AI with the sum running from the first term to the nth term. So what this means is that while the original sequence would be A1, A2, A3, A4, this new sequence is A1, A1 plus A2, A1 plus A2 plus A3, A1 plus A2 plus A3 plus A4, and so on. Hopefully you get the picture there. This new sequence is called the sequence of partial sums. And the nth term in the sequence is called the nth partial sum. Okay, now we're moving towards, well, we've got an infinite sequence, and so of course the natural thing to do is to take a limit. If the limit of this new sequence exists, then we call it the infinite sum of this original sequence because we're adding up all of the terms here. And the notation here is this. Now, we use this notation even if the limit doesn't exist. You would just say that this thing here doesn't exist. So in words, I would call this the infinite sum of AI, or I might be a bit sloppy and say the sum of AI from 1 to infinity. This second one is probably a bit less preferred because it chucks the word infinity around like it's just some other number, which it's not. Infinity is not a number, it's just a concept. So this one is probably more correct to say. All right, so if that limit does exist, you say the series converges, and if the limit does not exist, we say that the series diverges. So this is a general thing we should keep in mind here. In mathematics, the term sequence is not interchangeable with the term series. So a sequence is just an ordered collection of real numbers, whereas a series means you take a sequence and add up all of the terms in that original sequence. Not the same concept. So I noticed in the chat before, someone asked about series when they actually meant asking about sequences. Of course, they're very related concepts, but there is a distinction here, and we use these terms to mean different things. Okay, and just another thing, just like for sequences and limits, we don't have to insist that our sequences start at 1. We could have a look at a sequence starting at 3, say. In this case, our infinite sum would be the sum from I equals 3 to infinity, and that's how we denote it. So yes, it's not essential that we start at 1. It's convenient, but if we don't start at 1, then we emphasize that with this subscript there. All right, so that's that. Now, you might be surprised to learn, maybe not surprised to learn, that Mathematica can sometimes deal with infinite sums as well. So you may recall last time we were looking at putting into Mathematica the sum of n squared from n equals 1 to 100. And I think we got something like 1.6 maybe. It turns out that if you add all of these up in the way I specified in the last slide, this is actually convergent. And the sum turns out to be pi squared on 6. So what does this actually mean? So this input here, what that means, if you were writing that using the notation we just looked at, you'd write this like this. So of course, this infinity is the same as that infinity there. This 1 is the same as that 1 there. And this 1 on n squared is the same as this. And what this is saying is that pi squared on, that this sum is exactly equal to pi squared on 6. So just remember what that actually means. Remember, we introduce the new sequence, which is found by partially adding up this sum. So the first term in the sequence is 1. The next one is 1 plus 1 on 2 squared. The next one is 1 plus 1 on 3 squared. Sorry, no, forgot a term. 1 plus 1 on 4 plus 1 on 3 squared. And the next one is 1 plus 1 on 4 plus 1 on 9 plus 1 on 16, and so on. What this is saying, what Mathematica is actually telling us, is that the limit as n goes to infinity of these partial sums, this is exactly equal to pi squared on 6. Now, you might think it's a bit of a miracle that this special number pi managed to pop out in this infinite sum here. And yes, the reason pi squared on 6 pops out here, it is quite interesting. Again, unfortunately, not something I feel I'm in a position to quickly explain to you. And if you want to know the answer, well, I could probably direct you to the answer if you wanted. Okay, so that's more Mathematica. All right, now let's have a look. We're making our way towards some applications of this that you might find interesting. Okay, now, as I sort of indicated towards the very start of this session, sequences come up a lot when you're trying to approximate the true answer to a particular problem, and infinite sums come up for very similar reasons. Going back to our pi example, we can express pi as an infinite sum. We can express it as 3 plus 0.1 plus 0.04 and so on. So the idea is that each of the terms in this sum is just a particular decimal point of the expression for pi. And we know that this infinite sum converges. It converges to exactly pi. Okay, but this phenomenon is not just stuck with pi. This comes up all the time, where your goal is to find a particular solution to a problem, and the way you do it is by sort of making an initial guess as to what the solution should be, and then you incrementally add smaller and smaller parts to your answer, and hopefully you're getting arbitrarily close to the true answer. So this is the point I'm trying to make here. And actually, some of the elementary functions that you've seen already do this sort of thing. For example, the exponential function, where you look at e to the power of x, it turns out that can be expressed as an infinite sum. E to the x is given by 1 plus x on 1 factorial plus x squared on 2 factorial, and so on, using the sigma sum notation that we were just looking at. This is the same as the sum from n equals 0 all the way up to infinity. So I'm using the sloppy phrasing there. We look at x to the power of n divided by n factorial. So that's pretty interesting. And there's a similar expression you can write down for sine of x as well. It can also be expressed as an infinite sum. So that's nice. Now, question for the audience. If you feel up to it, please put your guess answer in the chat here. I'm looking at the sequence an from n equals 0 to infinity, where an is equal to -1 to the power of n. And my question is, if I do the infinite sum thing here, if I add all of these terms up, does the limit exist here? What do you think? So I've got someone suggesting diverges. Anyone else want to make a guess? Got a div? Yep. All right. Yep, 3 diverges. I guess maybe everyone's pretty convinced at this stage. Yes, it does diverge. And why is that? Well, the best way to see that perhaps is by writing out the partial sums. So remember, whether or not this converges or diverges depends entirely on whether or not this limit exists of these partial sum terms. But what are these partial sums? Well, the first term in the sequence is 1, so the first partial sum is 1. But the first 2 terms in the sequence are 1 and -1. If we add those up, we get 0. What about the next partial sum? Well, the first 3 terms are 1, -1, and 1. If we add all those up, we get 1. And so what you'll see is this infinite cycle of ones and zeros. And for reasons we've already described, this sequence does not exist. So that means that the infinite sum diverges here. So that's how you can use these partial sums to determine whether or not you're approaching anything here. All right. Maybe I'll stump you with this one. So yes, if you feel up to it, put your answers in the chat. Does this one converge or diverge? I'm perfectly happy for you to make guesses if you don't know. Okay, so we've got two converges here. Yes, it seems like everyone who's responding knows exactly what's happening here. Okay, maybe I'll try and make this a bit more difficult for you. How do you know it converges? What's the rough strategy going here? We've got someone suggesting it's divergent, but yes, I gave the game away. This one does actually converge, but now I want to see if you can give me a one or two word answer explaining why it converges. Maybe this is where I finally stumped you. Nope, someone got it. Okay, yep. Yes, very good. So, unless you're very familiar with these things, I'd say just looking at this straight out doesn't make it any easier for you. But the suggestion in the chat is to somehow manipulate this term to make it easier to see why it converges. Okay. So the underlying sequence we're dealing with here is the sequence from, sorry, this is the original sequence we're looking at. Wait a second. I think I've made a typo here. Yes, I've made a typo here. This should be 1 and that should be 0. Okay, so this first sentence here is basically just a cosmetic change. I'm saying that if I look at this, what I've got here is the sequence of 1 on n plus 1, n plus 2, starting from 0, going all the way up to infinity. Well, what does that look like? That looks like 1 divided by 0 plus 1 times 0 plus 2. The next term in the sequence is 1 on 2 times 3, and so on. This is actually the same as this sequence, 1 on n plus 1, starting from n equals 1 this time. Because, of course, you know, the first term is 1 divided by 1 times 2. The next term is 1 divided by 2 times 3, and so on. Now, you might wonder why on earth I would do this. Really, the motivation for me doing this is primarily cosmetic. I think that this looks a bit nicer than this. It doesn't really factor too much into the analysis, but it makes it simple. And, you know, if there are opportunities to simplify things, they should be taken where possible. Although in this case, it's not too essential. Okay, well, now what? Well, as was suggested in the chat, the fundamental thing to observe here is that 1 on n times n plus 1 is actually the same as 1 on n minus 1 on n plus 1. Now, where on earth did this come from? I'll get rid of the brackets here. They might be a bit too much. Yes, where on earth did this come from? Well, this is a fairly well-known identity. We'll come up later on in this semester. We'll come up with, this is part of a general method called the method of partial fractions. And it gives you a general method of, you know, splitting up fractions like this into sums of fractions of the individual terms in the denominators. Now, while I'll describe in greater detail later on in this course where this comes from, for the moment, I want you to see why it's true. And the reason it's true is because if you take this term and multiply top and bottom so that you have the same fraction, you'll end up with this, which of course is exactly equal to that. So that's where that all comes from. Now, why is that a handy observation to make here? Well, it allows us to rewrite this sum a bit. So remember, in order to work out whether this guy converges or diverges, we have to look at the partial sums. You take the sum of the first n of these terms, but because we've got this nice formula here, we're able to write it like that. Now that we've written it like this, we end up with something called a telescoping sum. Now, what do I mean by that? Well, let's just write out this sum. Well, the first term is 1 divided by 1 minus 1 on 2. That's straightforward enough. But the next term is 1 on 2 minus 1 divided by 3. And what you may notice is that these halves cancel out. As I keep going, I get plus a third minus a quarter. The thirds cancel out. And I can keep doing this all the way until the very end. This thing cancels out with what was left. And what I end up with is that Sn equals 1 minus 1 on n plus 1. So this is that term there. And now, in order to work out whether we get convergence, all we need to do is take a limit. All right, well, as n gets large, n plus 1 gets large, so 1 on n plus 1 gets arbitrarily small. Therefore, this term goes to 0, whereas this term stays at 1, and the limit ends up being 1. Okay, there you go. So this is an example of a telescoping sum. We were able to deduce that this series converges because we had a particularly nice way of expressing all of the terms in the underlying sequence. Okay, now we're going to get into some other theorems that are useful for us when we're looking at convergence of series. So this one's called the p-test for series. It concerns series that look like this. You're adding up all the terms of the form 1 divided by n to the p, where p is some number. In fact, it can be any real number for this. The p-test says that this is actually convergent as long as p is strictly bigger than 1. On the other hand, if p is less than or equal to 1, this series is always going to diverge. So that's a nice test there. Now, we've got another interesting test here. It's called the n-term test, or I think it might be more correct to say the nth term test. Now, this is a tricky one. It says that if you've got a series and it converges, so that means that the limit of the partial sums converge, that implies that the original sequence has to converge to 0. Now, I want you to be very careful with this one, because this is a mistake that students can make quite often. Now, my caution to you is this. This is not a test for convergence. You cannot use this test to make the claim that a particular series converges. However, you can use this test to conclude that a series diverges. Because another way of saying this, another way of saying the statement is that if the limit of this sequence as n goes to infinity does not equal 0, or even more generally, if it does not exist, then the sum is divergent. So if you've got an infinite sum and you notice that the terms go to 0, that's great. But if you want to know if it converges or not, you've got to do a bit more work. However, if you've got a series and you see that the limit of the underlying terms is not 0, then you can conclude straight out, yes, I know that this sum is not converging to 0. Sorry, I know that this infinite series is diverging. All right, let's get into an example. This is a nice example as it's more or less a combination of all of the tests we've seen previously. This one is called the harmonic series. So the underlying series is the sum, the underlying sequence is 1 on n, and we're adding up all of these terms from n equals 1 to infinity. The p-test that we just saw on the previous slide is applicable with p equals 1. So by p-test, this diverges. This diverges despite the fact that the limit of the underlying sequence is itself 0. So this illustrates why going to 0 is simply not enough to guarantee convergence of the underlying infinite sum. Now, even though we know this diverges by the p-test, in this particular case, there's actually a rather straightforward way of seeing why this series diverges. Maybe if you just look at this series, it's not exactly clear why this series diverges, because we're adding things up and the things we're adding up are getting smaller each time. So why isn't this converging to anything? Well, the reason is essentially as follows. If you look at what you're adding up, so this harmonic series is 1 plus a half plus a third plus a quarter and so on, we're going to do a bit of grouping. We're going to leave a half by itself. We're going to group a third and a quarter together. We're going to group 1/5, a sixth, a seventh, and an eighth together. And you group them up as follows. For all the powers of 2, you'd group all of the terms from 9 to 16 together. You'd group all of the terms from 17 to 32 comes next, I guess. And you group all of these together. Now, why is this nice? Well, if you're at the level of a quarter, a third is bigger than a quarter, and a quarter plus a quarter is a half. What about this stuff over here? Well, there are 4 of these terms here, and each of them is at least as big as an eighth, and 4/8 is another half. Over here, we've got another 8 terms, and all of them are bigger than a 16th. So that's another half. So the thing is that no matter how deep into the sequence you go, you'll always be able to find more terms that add to, yes, another half. So in the end, we're adding up things that are bigger than a half all the time. And of course, the partial sums then are at least as big as a half, 1, 3 halves, 2. That's not stopping. We keep adding a half. It's never slowing down. And so that means that the sequence is getting arbitrarily large. And so therefore this sum is divergent. So yes, that's an interesting example of a series there. Okay, so one more theorem before we'll get into an application in the last 10 minutes. Another very important class of series that you'll come across perhaps are the geometric series. So this concerns what happens if the underlying sequence we're looking at is an equals just some number a times some number to the power of n. R and a are both fixed, but of course n is running from 1 to infinity, or in this case, we're running from 0 to infinity. Now, if the absolute value of r is strictly less than 1, then we know that this infinite series actually converges. But even better than that, not only do we know that this series converges, but we actually have an explicit formula telling us what it's converging to purely in terms of a and r. This sort of series you may have seen in earlier maths courses. I won't be providing a proof of this result because it's a fairly well-known result, and it'd be good to, I think it'd be good to get straight into an application of this. Now, in the course reader, I found this application quite depressing. It concerned negative interest rates. So I know in some, I think in some European countries, they had negative interest rates at some point. The Reserve Bank of Australia, I don't think, has ever set interest rates to be negative in Australia. But this question is examining what happens if you try and store money in a bank that has negative interest. So what that means is that they are actually charging you to keep your money in their bank. It's a bizarre, I think it's a very bizarre fiscal policy, but I'm not an economist. I'm sure people have their reasons. But our scenario is this. Let's suppose that we've got a person who's earning 100, I didn't really put a units there, let's say $100 into an account, and let's say that this account is charging 5% interest per annum. So at the start of every year, they put $100 in, and at the start of the next year, they get charged 5% of whatever's in that bank at the moment. Okay. Now the question is, if you keep doing this, how much money are you actually going to have at the end of a given year? Well, how do we work that out? At the start of any given year, we're told in the question that we just put $100 in. But at the same time, the bank takes 5% interest off what was already there. So that's 0.95% of what was already there. What was already there? Well, recursively, we do the exact same thing. $100 we put in to start with, plus 0.95% of whatever was there the year before that. So if you keep doing this, you might be able to convince yourselves that what you end up with is this particular formula here. At the start of the n+1th year, the amount of money you have, let's be consistent with our use of dollars again. We have the sum from $100 times 0.95 to the power of I, and we're adding in and we're looking at I equals 0 to n. Yes, the bank is a robber in this particular situation, and what I find soul-crushing about this particular scenario is that even though you're putting $100 in at the start of every year, there is actually an upper bound to the amount of money you'll ever have. And the reason you can see that is by taking a limit. Let's take a limit and use this particular formula here. As another typo, as n goes to infinity, we can take a limit. What we're adding up is positive each time. So the amount of money in our bank is increasing, but it's not increasing like to infinity. You'd think that if you kept adding $100 into a bank, eventually that number would get as large as you wanted it. But no, in this particular context, the amount of money you'll ever have in your bank, it will never be more than $2,000. So that's not a good situation. And this is true in general. If a bank charges negative interest and the amount of money you're earning per year is bounded, then that you'll never get beyond a particular amount of money, even if you live to be as long as you wanted. You'll never get that much money without the bank changing its interest rates. So that's a bit depressing. We're not there in Australia yet. Maybe some of you live in countries where this is an issue. I wouldn't be sure. Okay, so that was 5.3. In the last 5 minutes, we might have time to look at what I think is a pretty interesting application of infinite series. Now, this is not exactly the application that was promised in the notes, but I think it's an interesting one nonetheless and quite useful from a data analysis perspective. Problem. This is called the set cover problem. So I'm going to describe it quite abstractly. let's say I've got a set of n elements. For simplicity, let's just call the elements 1, 2, 3, 4, all the way up to n. Now let's consider a collection of subsets. So you might, I think this was covered earlier, the power set. If you raise 2 to the power of a set, what that really means is just the power set. So it's the set of all subsets. Let's suppose we've got a collection of subsets so that if we take the union of everything in this set S, we get back to U. Now the question is, we know that if we take all of them, if we take all of the sets if we take all of the sets in S, we know that that gives us U. But is there an easier way of doing that? Is there a smaller number of subsets in S that we can take the union of and we still end up with U? Now, this was phrased in a particularly abstract way. So let's go through an example so I can tell you what I actually mean by this. So as an example, let's say that n is equal to 5. And let's say that our collection of subsets S, it consists of 4 subsets, number 1, number 2, number 3, and number 4. The first one contains the set 1, 2, 3. The second is 2, 4, and so on. You may notice that all of the numbers here, 1, 2, 3, 4, and 5, occur somewhere in this collection here. So if we take the union of everything here, we are going to get back to our set U. But the question is there a smaller number of sets here that we can do that will do the job? So just quickly, with the numbering of sets I've given there, what's a way of getting back to U by not, what's the smallest number of sets of S I need whose union is U? What are the sets that will do the job here? Maybe you could, yes, we've got the answer there. The set containing 1, 2, 3, union with the set containing 4, 5, that will do the job. Okay, great. So we're done. We've answered the question here. Now, even though you would always be able to, we've got a question here, why not 1, 2, 3, 4, 5? The reason is because the set containing 1, 2, 3, 4, 5 is not actually in S. So for the set cover problem, we're told ahead of time what sets we're allowed to combine. In terms of situations in which this would come up, I can't think of a great one off the top of my head, but this is a fairly well-known problem and has applications in a wide range of situations. Okay, now for a given collection, we'll always be able to do this. We'll always be able to find the minimal one, but you might notice that if the number here, if the number of sets we've got in here gets arbitrarily large, it's going to take a huge amount of time, even for a computer, to work out what the correct answer is. So instead, if this number n is extremely large, it's just not realistic to work out the exact answer. Instead, we're going to use the greedy algorithm. So the so-called greedy algorithm means you just take sets from S. At a given step, you search through all the sets of S and finds the one that has the most number of elements that you haven't already included, and then you include that one. So how does this greedy algorithm work? Well, let's have a look at the question we just did. We're trying to cover this set using some of the sets here. What does the greedy algorithm do? Well, the first set we're going to include, since we haven't included anything yet, we're just going to include the subset which has the largest number of elements. That's obviously this guy here. So the first set we choose is 1, 2, 3. Well, what about the next set? Which of these are we going to include? Well, this one has the largest number of elements that hasn't already been touched. So we include that one. So in this case, the greedy algorithm does give us the correct answer, but it doesn't always. Here's an example. This time, our set has 6 elements, and our set S contains 3 of them. One of them contains the middle 4 elements, the second contains the first 3, and the third contains the last 4. Now, what will the greedy algorithm do? The greedy algorithm will first select this one here because it has the largest number of unused elements. The second and third sets have to be 1, 2, 3, and 4, 5, 6. So we can see that the greedy algorithm, it actually it returned all of the sets. It says all of the sets will do it. And while that is correct, it's not the correct answer that we're after, because we only need to use these 2 sets to get the answer. So in general, it's not going to give you the exact answer. And so the natural question here is, how bad is it? How much worse is the greedy algorithm answer compared to what the correct answer actually is? And interestingly enough, this can be described in terms of sums and infinite sums. In general, if you've got n elements in your original set U, then the answer you get using the greedy algorithm could be as bad as hn times the number of sets needed for the correct answer. Now, you may recall that as n goes to infinity, this number here, hn, goes to infinity as well. So what that means is that there is no upper limit to how bad the greedy algorithm answer is compared to the true correct answer. So yes, well, I'm going to leave it there. I'm sorry I went a bit over time, but I thought it would be good for you guys to see an application. So yes, we'll leave it there for this week. The mid-semester break is next week, and hopefully I'll see you all the week after as we continue. So I suspect many of you might wonder about the slides. So yes, as I suggested at the start of the lecture, I will be uploading these slides to GitHub. I won't do it tonight because it's almost bedtime for me, but I will get onto that sometime tomorrow if everything works out. All right, thanks very much for your time, everyone. I'll leave it there. Yes, please feel free to stick around and ask questions if you need. And I'll stop the recording now. Thanks, everyone.